Yes, I guess we can start. Welcome to the live session for week 9 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a PhD student from IIT Kharagpur, and I'll be assisting you in solving week 9 assignment problem that will be similar to the problems that has been given to you in the week 9 assignments. So we'll be covering some of the concepts and then also solving some of the problems so that it can help you in solving the assignments. So as we are approaching towards the end of the course, we have already covered all the device physics and all, and we have moved towards the models, different models. So in the last class, so this complete till week 6 was the physics and the devices that we will be studying, and we have covered in quite deep the MOSFET devices. And then we started with some of the transport theories. So we started with semi-classical transport. We also went towards the BT equations, and from the in the last week in this week 8 lecture we discussed some of the DD models, that is the drift diffusion models, and we derived the diffusion part of the current, that is something due to the diffusion of the electrons, and there is another component which is a drift part, that is due to the applied electric field. So till here we have already covered, and in this particular week we have the further drift diffusion model, some of the generation and recombination models that were left in the previous class, such as the exciton model. So I'll maybe give a very brief about the exciton based recombination and generation. Then there is SRH model, which is Shockley-Reed-Hall. So we'll see what are some of the boundary condition. We have already covered the Dirichlet and the Newman boundary condition in the previous class, and then some of the Newton-Raphson method and iteration method. So yeah, these are some of the application based topics, and we'll be covering the initially we'll be covering the derivation of this continuity equation that is related to the drift diffusion model, uh, and then we can see some of the problems, relevant problems for that. So if you remember in the last class we studied about the recombination and generation rate. Let me give you a very quick overview of that, I mean quick revision, so that we can solve. So let's say we have any bar or any device which is something like this. It is happening, some recombination generation is happening inside this, some flow of electron is happening, so the flux that is going out is coming out of the device. So for electron, let's say, so we establish that the change with respect to the time in total, it can be due to the current through it, or it can be due to the recombination generation that are happening, or it can be due to any other process that we are not bothered about. I mean, this is not the majority part, the main part is these two only. Similarly, for holes we can write the same equations, just the n will be replaced by p. So the change in rate of holes with respect to the time can be due to the current, can be due to the recombination generation, or any other process. But what we established in the previous classes, we know that at thermal equilibrium the overall current AC comes out to be 0, because at thermal equilibrium there is no net charge. So dN by dt total is 0, and this also implies that at equilibrium all the components are 0. That is, the current component is also 0. The recombination generation is also not happening at equilibrium, so all of them are 0. Similarly for holes, so this is for electrons. For holes we can replace the p by n. Then we establish that if we move out of equilibrium, then what can happen. So if you move out of equilibrium, then the current is introduced, so this component rises, I mean this component has a certain value, because we have established that in the p-n junction diagram also, that we have certain Fermi level difference that can give rise to some electric field and enhance, and in turn the current also. So yeah, so let's say we have moved out of equilibrium, but steady state condition is there. So in this lecture we'll be studying about these four conditions that we discussed in the previous class. There was a steady state, there was low level injection, then there were few more things, so that we'll be discussing here. So in steady state means that the individual parameters, so let's say this holds, so what it means is that the individual parameters may not be equals to 0, may, but the total concentration, because we are in steady state, but the total concentration change is equals to 0, because we have maintained the steady state, we are not in the any transient state right now. So what does it mean? It means that at steady state, what we have is we can have a total response of dn by dt, it can be 0, but the individual components such as the current one or even the recombination generation one is not equals to 0. This is what it means. Same goes for holes if I replace p with n, or n with p, sorry. So this is what do we mean by the steady state, but we can also neglect the other processes. Uh, so let's say if we neglect two processes and let's say we focus only on the recombination reaction, because that is a major focus for this particular lecture. So we can write that dn by dt total for now, because since we are not focusing on any other process, so it can be due to the recombination generation. So this is the overall, and it is basically the generation rate minus the recombination rate, because whatever the uh, cytons or whatever the electrons are getting generated are getting recombined with some of the holes. That is the electron hole pair recombination and generation is happening. So using this, because we are in steady state, what we can write is Gn is equals to Rn. Same goes with dp by dt, and this will imply that Gp will be equals to Rp. So what we can say, I mean, this is what we concluded in the last class, that at steady state, the generation rate of excess carriers is equals to the recombination rate of excess carriers. So mathematically what I'm trying to say is, so if we have, let's say, recombination generation, or let's say first focus on the recombination. So let's say we have n, where n naught is a thermal equilibrium in electron concentration, and delta n are the excess electron concentration. Similarly for p, p naught at equilibrium and delta p at the excess hole concentration. So this is out of equilibrium. Whatever is denoted with naught is in equilibrium. So for low level injection, I mean, if the carriers that are getting injected are very low, so we have given this assumption that it is low level injection. So delta n or delta p is very less than n naught, and this is for a n type semiconductor. Similarly, delta n and delta p will be very less than p naught for a p type semiconductor. So recombination is, as we discussed, it is only due to the minority carriers. So the recombination rate can be given by, let's say this is denoted by R, this will be delta n, which are the minority carriers for p type semiconductor, by the time constant. So this n will be for p type, because we have minority carriers n in the p type, and similarly delta p by tau p, which is for n type semiconductors. So we need to remember that this tau n and tau p are nothing but the minority carrier lifetime, not the majority. So n will be for electrons and p will be for holes. So for electron and holes I'm writing. What I'm trying to say is that, let's say at equilibrium we have n naught as 15 and p naught as, let's say, 5 only. So this is a n type semiconductor. So delta n is equals to delta p at equilibrium. So what we can say that if I now try to, So this is the excess carriers that are being introduced. So if I try to write 10 raised by 5 plus 5, so it becomes twice of the p type concentration. But same if I do for n type, that is if I try to calculate n, it remains the same because 10 per 5 is negligible as compared to this. So it is approximately 15 per centimeter cube only. So that is why we focus towards the minority carriers concentration. So n type we have the minority carriers. Same we can go for majority carrier lifetime, but yeah, that is not of much relevance. So yeah, we can skip this particular thing. Now the main thing that we will be deriving further on is the continuity equation. So what we have is, as I said, we let's say have a certain bar. The inside going current SC is, let's say I'm denoting for electrons only. So at the last point, so let's say this is of length dx, starting is x and end is dx. Sorry, it will be x plus dx. So at this point it will be x plus dx, and there are some recombination generation in some method that is happening. And let's say A is the cross sectional area. So volume is, since A is the area and the width of this is dx, so A dot dx will be the cross sectional area. So continuity equation, first of all, it is very useful in finding the net rate of charge concentration, charge carrier concentration when everything is happening. So it also takes account drift, it also takes account into the diffusion part, and also takes the recombination and generation part. So let's see them one by one, and then let's see how we can derive that. So the first thing is the rate at which electrons are entering into the sample. So we can write, so these can be the current area by charge. So this is nothing but the rate, because charge is nothing but current per unit time. So since we are talking about electrons, so let's say we have a negative charge. Similarly, I can write that rate at which electrons now are leaving the samples. So it is leaving at x plus dx. So it will be Jn at x plus dx. The area will be the same, and minus q will be the charge. So what else can be there? Now the electron generation and recombination can happen. So rate at which electrons are generated. So it is nothing but the generation rate multiplied by the volume. Similarly, rate at which holes are generated. So it is nothing but Rn AdX. So the net rate now. So we have considered everything, the recombination generation and as well as the drift diffusion part. So the rate at which now, or the net rate of electron concentration can be, so we were discussing that the dN by dt total is the sum of everything. So it can be due to the current, it can be due to the recombination and any other process I am currently neglecting. So what I can write it, if I can just multiply it by the volume at both the sides. So it is nothing but due to the current rate changes, Jnx times A by minus Q and minus the Jnx at A by minus Q. Sorry, so it will be the leaving part, which should be x plus dx, and plus again the volume multiplication will be there, so it is Gn minus Rn. So this is what we can solve, and this is solved using the Taylor series expansion that we discussed in the last class. So using Taylor series expansion, so what I can say is, basically let me write the basic formula. So jn x plus dx will be nothing but jn at x plus uh, 1 factorial. I mean 1 factorial is 1 only, so I'm not writing. So djn by dx times dx, because this, let's say this is a, so x plus a will be at x, then at x dx, so multiplied by a only. So hence in the above equation we can substitute this, and will what we'll get is dn by dt a dot dx, which is the LHS from the beginning. It will be, if I can take a by minus q common, so it will be jnx, and I am replacing this jnx plus dx from the Taylor series like this term. So this is plus djnx over dx, and the rest is same, that is the gn a dot dx minus rn a dot dx. Again, on more simplifying, this jn will get cancelled out, so this and this will get cancelled out, and we are left with this minus term, which is minus djnx over dx plus a rn, sorry, not rn, gn minus rn over dx. So now both the terms have dx, so what I can do is I can, in the, sorry, in the LHS we have this a dot dx from the beginning, so I can cancel this a dot dx from here also and from here also. So what I can write now is dn over dt is nothing but 1 by q, so this minus and minus is also cancelling out, is equals to djn over x over dx plus gn minus rn. Let's say this is equation 1, and we know that this jn, because we have now established that what is the drift and diffusion part. So for the electrons it will be nq mu n e plus the diffusion part, that is q dn over dx. So we can put this into this differential part and get the final continuity equation for electrons. So if I put it, so it will be nothing but, so let me simplify it here only. So this thing, if I make divided by q at both the sides, so 1 by q jnx will be mu n e dn over dx, then plus, okay, not, okay, sorry, so it will be n mu n e plus dn over dx. Now what I want is, I want the differentiation of this for this particular continuity equation, so let me do that. It is 1 by q djn over dx, so the differentiation will be 1 by 1, so we'll apply the product rule. So mu n e is constant for one part, so it will be dn over dx, plus now n mu n is constant, it will be d over dx, and this term is nothing but d2n over dx2. So this is what we'll put in the equation 1 to get the final content equation, and it will come out to be dn over dt is mu n e dn over dx plus n mu n de over dx plus dn d2n over dx2 and plus the gn minus rn. So this is the continuity equation for electrons. Now for hole we can like redo the whole process, and we only need to be careful about the signs. So let's do it quickly. Similarly for holes, we can have a similar bar in which we are only focusing on the hole concentration, which is at x here, and it is jp x plus dx here. Same, the cross sectional area is a and the length is dx, and the recombination is happening. So Let me skip to the part of the continuity which is dp by dt. I multiplied by a dot dx at both the sides, and on multiplying what I'm getting is jp x. Okay, so yeah, let me write the equation first and then I'll not write the Taylor series expansion part. I'll only write the solution. So this is again q, so now this will be plus q because of the holes, plus again gp adx minus rp adx. And now doing the Taylor series expansion, I'll reach to the x plus dx terms. From that the jpx term will get cancelled out and I'll reach to again the same thing, minus 1 by q dp over dx, not djp over dx plus gp minus rp. And again we know that jp is p mu p qe plus the dp over dx. Sorry, it will be minus because in the diffusion term we have the minus q in this. Again we can do the differentiation and just put in the continuity equation. What we'll reap is, we'll reap the continuity equation for holes. So that is nothing but dp over dt is minus p mu pe, not e. So p mu p, one of will be the electric field, minus mu pe, second one will be the concentration, then plus the second differential of T2p over dx2 plus the gp minus rp. So this is nothing but the continuity equation for holes. So now from this we take all the several assumptions and we'll try to calculate the final concentration or the excess carrier concentration for the different cases. Like we can take no light, that means there is no recombination generation. We can take the steady state. We can also take there is no concentration gradient, and we can also uh, derive those things. So let's try to do it. So let's take the first case as minority carriers with low level injection. So the approximations that can be taken here is, first is no electric field. That is a dE by dx term that we have is can be made 0. So E is 0. dE by dx will also be 0. The second assumption can be equilibrium concentration do not change with x. That is the concentration do not change with x. Basically dN over dx or dP over dx can be 0. The third assumption or the approximation can we take is the low level injection that I have already explained in the previous part. So now for these things, let's say we are talking about an n-type semiconductor for simplicity. So in this the minority carriers will be the holes, right? So if the minority carriers are holes, then we'll be calculating the excess carrier concentration of the minority carriers, that is delta P. And since we are talking about low level injection, so we know that delta P will be very less than n naught. So if I differentiate it both the sides with respect to time, so P naught is constant with respect to time because we are taking the equilibrium concentration is constant, plus it will be d delta P over dt. Similarly for position it will be dp over dx, so it is still constant and it is d delta P over dx. So now we have just derived that the continuity equation for hole is, so what I can write is d delta P over dt because we are trying to calculate the delta P, that is the excess carriers holes. So it will be dp, since the the E term will get cancelled out because electric field is 0. That is the first assumption that we have made. The second assumption that we have made is dp over dx or d delta p over dx is 0. That is the so for this I can write dp over dx because we are talking about the continuity equation of holes. So the first two terms will go away and we are left with this dx2 and plus the gp minus rp, and rp is nothing but delta p over tau p. We need to solve this particular differential equation to calculate the minority carriers excess concentration. So now let's suppose similarly we are talking now about a p-type semiconductor. So again we know that this delta n will be very less than p naught because in p-type the minority carriers at equilibrium will be p naught. So we can write the same thing about the n-type, which is dn over dt is nothing but d delta n over dt, and dn over dx sorry is nothing but 0 plus d del n over dx. So again we can write the continuity equation for electrons also in the same way that we write for road for holes. So d, it will be nothing but dn d2 delta n over dx2 and plus the recombination generation, so gn minus rn. Rn is nothing but delta n over tau n. So using these two equations, now let's take the cases one by one to calculate the delta n or delta p. Let's I'm taking delta n for all the special cases. You can do the delta p by yourself. I mean the formulas will be same as always. So the special case one is steady state I'm taking and no light. So no light means no generation. So Gn is 0 first of all. Steady state means in the initial part I told you that the dn over dt, the total component is 0. So these are the two things. So now we'll do the putting up these two things. So this will be 0 and this will become 0. Yeah. So we'll get a simple double differential equation that we can calculate easily. Let's try to do that. So the modified continuity equation will now will look like so it will be 0 and the second term is dn d2 del n over dx2 plus 0 because there is no light minus the recombination is del n over tau n. So what I can write now is del 2 tau n over dx2 is del n over dn tau n. So dn is again constant. So this is a variable and this is a like equation which is, let's say, d2x over d not x. It is like a equation which is d2y over dx2 is x over some constant, let's say a. So it is easily solvable. This is a direct differential equation and ln we know. So this part we, if you remember, we write about the diffusion length, that is ln, which is dn tau n, which is called the diffusion length for electrons. So if you try to solve this is a direct equation. The solutions comes out to be del n comes out to be a times of sorry a times of exponential of minus x by ln plus b times of exponential of x by ln, where a and b are constants. So this is the general solution for equation, let's say equation 1. So this is the general solution for 1. So this is the first case that we are talking about. Similarly, further the second case could be the special case 2. So in this, what we can take is we can take no concentration gradient and still no light. So no light means Gn is 0, right? And no concentration gradient means there is no concentration change with respect to x. So dn over dx is 0. That means d del n over dx is 0, because that is what we are figuring out. So now there is no steady state, so we can give this term a finite term. The second term, which was d2 of del n over dx2, so this is now 0 because, yeah, this is the lab. uh, Give me a moment. Sign in कहीं पे देखो तो सुनिए check करते हैं. क्या नाम है उनका? अनंत. देखो नाम. हाँ देखिए. तो मैं नहीं आता हूँ, वही दूसरे आते हैं इसलिए. Thank you. Yeah, so d2 del n over dt, so this term now will become 0 because we have taken no concentration gradient, plus gn minus, let me write the whole equation. So what I am now saying is this will become 0 because no concentration gradient, no light. So this is a very straightforward equation, that is d dt is nothing but, so this is straight away first order differential equation, and the log is a solution. So it is, the del n will come out to be some del n at 0, that is some constant, multiplied by minus t by tau n. So this is a general solution for the case when there is no concentration gradient and there is no light. The third special case that we can take is, we are also taking the steady state. Let me write special case 3. We are also taking the steady state now, and instead of no light we are taking no concentration gradient. That is the only possible combination left. We cannot make everything 0. So this means that d del n over dt will be 0. This means that d del n over del x will be 0, and gn will have some finite term. So using the continuity equation, so 0 will be the dt term will be 0. So the second order term will also be 0 plus gn minus rn, right? So in this case, as we have already seen, the generation rate becomes equals to that of the recombination rate, and from this we can calculate the del n, which is gn times tau n. So these are the three special cases that we are supposed to cover in the derivation part also. So let's try to do a numerical on this. Maybe I'll cover maybe 2 cases, and then the third you can see by yourself. So I'll cover, let's do a numerical out of it. The question says that consider a bar of p-type silicon. So as soon as we know that it is a p-type, so we are calculating del n, because we are only interested in the minority carrier excess concentration. So it says that the p-type semiconductor or the silicon is doped with 3 times 10 is per 15 per centimeter cube at T is equals to 300 Kelvin. So it is a room temperature. The applied electric field is 0. So this is the first Q in the question. The light source is incident on the end of the p type as shown below. So let's say this is a semiconductor, and this is how the light is incident. This is x equals to 0, this is at x, and this is some light, and it is p type. The excess carrier concentration generated at x is equals to 0. So at x equals to 0, so excess carriers for p type concentration is, so del p0 you can write, which is nothing but 10 is for 13 per centimeter cube. It is already given in the question. So assume the following parameters. So mu n is given, that is mobility, which is 1200 per centimeter square per volt second. Then we have the tau n, that is the minority carrier's lifetime. So it is 0.5 microseconds. So I'm writing it in seconds. The mu p is also given, is 400 centimeter square per volt second. The tau p is 1.1 microseconds. So what we need to calculate is calculate electron diffusion current density. Electron diffusion current density at, so this is the keyword now, at steady state. So this is a problem. Maybe you can take 5 minutes and then I'll try to solve it by myself also. Okay, so hope you have given it a try. So let me try to solve it. So there are two keywords here. So the question is asking at steady state the electric field is zero and there is some light incident. So Gn So what it says that a light is incident on the end of the semiconductor as shown below. So at x equals to 0, the excess carrier concentration is this. So what we need to find is we need to find the electron diffusion current density. So the electron diffusion current density is nothing but the Jn, and it is the diffusion part. So what we need to find is q dp, sorry, not dp but dn over dx. So this is ultimately what we need to find. So let's start with the continuity equation only, because we know that some of the terms are 0 in that. So it is in steady state, that means this term will be 0. The second term is the electric field term. So I'm not writing the complete term because electric field is 0 in the question, plus mu n e, the dn over dx term. So this will is again 0 because the electric field is given 0 in the question. The only concentration gradient will be the d2 n over dx2, plus there is no light, and minus recombination rate. So this will reach to one of the special case that I have discussed in the above slides. So what it will reap is it will reap to d2. So I'm replacing n with delta n because those are the excess carriers, is equals to del n over ln square, and this ln is again under root dou dn tau n. So this is already been discussed, and the solution of this came out to be, at x came out to be a exponential of minus x by ln plus b exponential of x by ln. So now we need to find the del n to find the Jn. So we will find out based upon the given conditions. So let's say if I talk about at infinite potential or the infinite position, all the minorities will remain, right? Because at infinite potential there cannot be any minority left. So if I try to put this, so at x equals to infinity, this term will become by infinity. So this whole term will become 0 and this term will become infinite. So what I can write is 0 is nothing but a exponential of minus infinity plus b exponential of infinity. And now to satisfy this, there is only ways b will be 0. So from this, we have reduced the equation to one of the term, which is a exponential of minus x by ln. Now it is given in the question that at x equals to 0, the del n at 0 is 10 raised to power 13 per centimeter cube. So this is, I have already given here that the excess carrier concentration is this. So we can use the initial condition to calculate the A. So it will come out to be, final equation is del n naught exponential of minus x by ln. So ln we can find out using dn tau n, and these two are also given in the problem. So dn is 31.2 and this is 5 times 10 to the power minus 7, that is 0.1 microsecond. So if you try to solve it, this is 3.94 minus 3 centimeter. So now you know everything. Now the question has asked for the diffusion current density to find. We need to find the diffusion current density. So now we can do that quickly. What is the diffusion current density? This is the diffusion part is q dn over dx, and we are only talking about the minority carrier. So what we can write is, sorry, q dn, n will be now del n. We have this equation, we can differentiate it one and we can easily find everything. So q will be 1.6 minus 19, dn is 31.2, and the differentiation of that particular term will be, so exponential x will be so it will be into minus 1 by lx or ln exponential of minus x by ln. So I've just differentiated it once. So the Jn will be, if you put everything, it is minus 1.6 10 is for minus 19 times 31.2 times 10 is for 13 over ln. We know ln, we have just calculated, is 3.94 10 minus 3 centimeter, and it is exponential of x by 3.94 10 is per minus 3. So if you try to find out, so on solving the coefficient term, it will come out to be minus 12.67 exponential of minus x by ln. So ln is again 3.94, and this is in milliamps per, so there is 1 milli left, so it is milliamps per centimeter square. So this is the current diffusion current density that was asked in the question. So it is a function of x because the concentration gradient is not zero, and this is how you find it. So for each of the special case that I have discussed, so the special case one was when it is steady state and there is no light. So this was the numerical for this particular case. So in this derivation we came to know that this can be the general solution. And now based upon the given problem we came to know that either A is 0 or B is 0. So we came to know that B is 0, and from that we have calculated the diffusion current density. Now in the special case 2 we had no concentration gradient and no light. So let's try to do one of the numerical for this, and uh, after doing this the last case I'll skip maybe because that is very straightforward, or we can do the uh, maybe the third case. So let's see the numerical looks like, and accordingly we need to check which case is that. So the next problem maybe I can write quickly. So we have a silicon, temperature is again 300K. We have n type, so I'm writing directly nd is given as 5 times per 17. It is illuminated uniformly, so it is illuminated now uniformly such that 10 is per 14 electron hole pair generation is taking place per centimeter cube. So this is nothing but the generation rate Gn. And the incident radiation is turned off, so there is no radiation. So if I try to calculate the minority carrier concentration, the Gp will be 0. Assume low level injection is always the case, and the intrinsic carrier concentration Ni is given, that we all know that it is 10 per 10, and the minority hole carrier lifetime is given as 50 nanoseconds. So now the question is the time at which minority carrier hole concentration reaches 10% of its initial value is how many nanoseconds. So this is the particular problem. So let me solve it by myself. Sorry. So now there are three things in this. There is low level injection, there is no light. So again let's start with the continuity equation. So it is changing with time, but there is no electric field, so the first term will be 0. Okay, so let me write it. Mu p dE over dx. Second term is minus mu p e dp over dt. So since it is steady state, so this term will also be 0. Sorry, this is dx, not dt. Then the third term is dp d2p over dx2. So there is no concentration gradient. This term will also be 0. The light is also stopped, minus rn, oh sorry, rp. So we are only left with these two terms, that is dp by dt and rp. So this is the special case 3. So if you try to solve it, I mean we have already solved it in the derivation. Let me give you some more overview because otherwise. So the total concentration we have discussed, it is P naught plus delta P. From this dP over dt will become d del P over dt. Similarly, d2P over dx2 is 0, that I have already cancelled, so yeah, we can leave this. Gp is 0, I have already told you that the light is turned off. So using this, what I can write is d, so from for P I am replacing del P over dt is what we are left with minus rp, and rp is nothing but the time constant, which is minus del P over tau P. So this is the first order equation, very straightforward to solve. It is like equation dy over dt is y over some constant, so let's say a. So this is dy by y over some 1 by a dt. So if you try to integrate, so this is a logarithmic solution and the exponential solution will come out. I have done the derivation in the first part of the class. So it will come out to be ln of del p is minus t over tau p plus ln of at 0 also we need to write. So there is some constant and this will come out to be del p naught exponential of minus t over tau p. Now the question is not asking the excess carrier concentration, it is asking something different. And also the generation rate is also given, so that is stands for 14. Yeah, so this is the final solution of the excess carrier concentration. Now the question is saying the time at which the minority carrier whole concentration reaches 10% of its initial value. So the initial value is this, and when it reaches the 10% of del p naught, what will be the time? So that is very easy now. So let's say at t is equals to t1, the del p becomes 10% of del p naught. This is what the question is asking. So what is that time? So this is very easy now because we know both the sides. So this I will replace with this, which is del p naught exponential of minus t over tau p, and 10% that is 0.1 times of del p naught. So this will get cancelled out, and what we are left with is, if I take log on both the sides, so it is 0.1 and this is minus t1 over tau p. So ln 0.1 is so t1 is that time, so tau p is 2.303 is the minus term will get cancelled out because of 0.1 and multiplied by the tau p, and tau p is given as 50 nanoseconds in the problem. If I'm not wrong, what is the tau p? Yeah, it is 50 nanoseconds. So t1 will be 2.303 times 50 nanoseconds. So this is the time at which the excess carrier concentration becomes 10% of its initial value. So 23, 5, 15, 15, 1, 1, 5, point 129 nanoseconds. So yeah, I mean these are all the initial, oh, sorry, not initial, but the special cases that are covered in the drift diffusion model. So let me again quickly try to tell what were the cases. So the first case was is that. So the first case was when there was steady state and no light. The second case was when there was no concentration gradient and no light. The third case was a steady state and no concentration gradient. So like there can be three possible combinations that I have already covered. And using these three combinations, we have covered two different numericals. The third one is very straightforward. I mean, that is not even an equation, so I'm not covering that. So the thing left is one topic, that is the recombination generation through exciton that give rise to the SRH model. So let me try to explain it very quickly. Yeah. So in the previous class, I explained you one of the recombination that is due to the impact ionization, and we named that recombination as Auger recombination, if you remember, in which the impact ionization is helping in causing that recombination generation. So there is one more RG method that we are left with. So it is covered in this particular week. That is the recombination generation through excitons. So these are some special, what to say, some special material, not material, but atoms. So we have seen that the EV is completely full, and the conduction band is always empty. So what is a exciton is, let's say there is a vacancy gets created over here due to some application of energy. So um, this electron, when it goes from conduction band to, sorry, from valence band to conduction band, so this hole is always remains associated with it. So this particular particle is exciton. Like this hole is also associated with this particular particle. So this is EV, this is EC. So let's say it has some electrons for now, and due to some energy, the hole is also gets associated with this particular electron. So this particle is called exciton. And again, there can be an electron which can attract, or which can what to say, interact with this. So again, this is exciton. So basically, exciton is an entity where you have an electron and hole. Let me write. So exciton is where you have an electron and hole free, that is not in the valence band, but they are coupled to each other. And this pair can easily diffuse, I mean, because it is always charge neutral, because it is a electron and a hole, so it can diffuse and move through the semiconductor. So if I try to tell you the process of RG through exciton, so here electrons are excited from valence band, but they are still bound to the hole, as I have made this exciton diagram. Although they are free from influence of the lattice atoms, because once they have crossed the valence band, they are free from the influence of the lattice atoms, and they can be energized to create pure electron and hole pairs, probably by applying some of the photonic energy or electric field. And this is how the recombination generation takes place in this. And this is some of the principle of SRH recombination, or SRH model I can write. So now let's try to quickly wrap up some of the problems. So in case
So
of,
here, Anant, I have one question.
yes, yes,
Excitons, both this hole and the electron will be held together, and it will be moving in the lattice.
no, lattice is this. Once the electron, or the once the valence
Uh-huh.
band gets sufficient energy, this electron, what happens, I mean, in general, is this electron comes out of the valence band and goes to the conduction band.
Mhm.
And there is nothing here, there is a hole is not a particle, hole is just a vacancy. So what happens is this vacancy is also associated, gets associated to this electron. So this is exciton.
Okay.
Yeah. So this is not a particle, I mean, this is just a neutral thing. That is what we are trying to explain in some way. Hole is never a particle. This is a
Okay.
neutral thing that is getting moving from conduction to valence. So using that, we are doing the recombination and generation. Like this electron can come back to the conduction,
Mm.
sorry, back from the conduction to, let's say, valence, and there is a hole associated. So this can also create exciton. So this is a recombination and this is a generation, something like that.
Okay.
Yeah.
Thanks.
Oh, in case of band to band recombination, how increasing the doping concentration? Okay, so this is easy. So if we increase the doping concentration, let me, is that, yeah. So we have just seen that it is asking how increasing the doping concentration. So we have seen that, let's say we have maybe n type semiconductor. So in that, the delta n, or the total n, was n naught plus del n, and the p naught was, sorry, p was p plus delta p. So what we are considering is, uh, now we can see the options. So it remains constant. What is the question? How increasing the career lifetime? Okay. So lifetime is basically, we know that, let's say if I talk about the recombination rate only. So it was, well, it was del n over tau n. How does the doping concentration affect a low level injection? So this is what we find out, and if we increase the doping, so what will happen? It will, the time. So time will be del n over Rn. So now it is saying that if we increase the doping, what will happen to the carrier lifetime? Okay, it is not clear if it is asking for minority or majority. So there can be two things here. So for minority, the lifetime should increase, and for majority, that will be the opposite of this. So majority lifetime also we can find. I have not covered that, but yeah, it can be easily calculated from ni. Np is equals to ni square. So what I'm trying to say is, so del p over tau n is del p over tau p. Sorry, not del p. So these are the two lifetimes of the minority carriers. Now similarly, if we want to find out the majority, so let's say uh, tau n is now the majority and tau p is the majority carrier lifetime of holes. So if I go with this notation, then what I can write is del n. Del n is minority, so np is equals to ni square. So p will become ni square over n. So if I try to write that, so n over tau n, so from this I'm writing n is a majority, and p over tau p, so p will become ni square over nd, right, times 1 over tau p. And from this, the tau n will become some formula, I mean, will come out n nd over ni squared tau p. Yeah, something like that will come out, and it will become the inverse of this. So for minority it will increase, for majority it will decrease. So it is not clear. So whatever the, I mean, from the question perspective, this can be the probable answer. Now what we have is, what recombination mechanism involves combination of electron and a hole bound together? So this is the exciton problem, right? So this is, I mean, direct.
Yes.
Option B is the correct answer, exciton recombination. Why does exciton recombination typically release radiation lower than that of band gap? So yeah, because if we increase more than that of band gap, it will become a direct recombination generation. So what we want is, we want something in between. So that is the case. Now let's see the option. Exciton release energy equal, no. Carrier net charge, no. There is a charge, but they are neutral. I mean, both the electron and a hole have a charge, but they are neutral because the binding energy of exciton must overcome. Yeah. So option C is the correct answer directly. Next is calculate the SRH recombination rate. So recombination rate only we need to find for n-type semiconductor. Excess hole concentration is given, minority lifetime is given. So this is direct only. Oh, sorry. Did it go? Mm, yeah. So for the minority carriers lifetime, it will be del p over tau p. I guess both of them are given. Yeah. So del p is 90, tau p is 2 microseconds. It is 19 per meter cube. Okay. So per meter means centimeter will be more. No. Options are in both. So it is 10 is for minus 6 per centimeter cube. I don't know if I'm right or wrong. So 10 is for 13 over 2 micro. So this will give 0.5 into 10 is for 19 per centimeter cube per second. The option. This is option. If I write plus 6, then there will be no option. Yeah, so this is right then. So the correct answer will be option C. Make sense?
Mhm.
Yeah. Similarly, we have a n-type semiconductor material with a capture coefficient. So there is a capture coefficient also associated with that. So let me write the formula for this. For this, the minority carriers, so we have n-type, so this will be tau p. The formula is nothing but 1 over capture coefficient, whatever the coefficient is given, multiplied by the nt, that is the trap density. So these are our straight questions. So it is 1 over capture is minus 14. Again, it is in meter. So meter, so we can write it is per meter cube, so it is plus 6. Sorry, it is in meter cube, so it is plus 6 in centimeter, and 2 cross 10 for 14. So this will get cancelled out. 1 by 2, that is 0.5 microsecond. You need to recheck. I don't know the exact answer, but I think the calculation wise 0.5 microsecond is the correct answer. Okay, so we have one absorption coefficient question. So this is a complete different topic, that is optical adsorption or absorption. Maybe I'll let you know the formula for this. So the intensity which get absorbed is exponentially related to the this you might have seen in the optical absorption problem. I don't know if which part of the course covers this, but yeah, this is the direct formula. So the intensity is, you need to find out the absorption coefficient, which is alpha in this case, if 2 millimeter thick semiconductor reduces the intensity by 0.1. So it reduces it by 1/10. So what it does it mean is the intensity has become 0.1 of I naught and exponential of alpha x. So from this you can find out alpha, which is the thickness is 2 millimeters. So alpha is width, alpha x is minus ln 0.1. So alpha will be 2.303 times 2 millimeter, which is 1.15 something something millimeter inverse. Is there any option? Yeah, option C is the correct answer. So if you want, I can go in details of this optical absorption in the next lecture, but it will take a lot of time. So for now, we can do with the formula. Then we have given uniform illumination with light. So we have now given some light resulting in an optical generation rate of 10 raised per 20 per centimeter cube per second in a p-type semiconductor. So yeah, so a p-type semiconductor. What is the distance between the quasi Fermi level and intrinsic? So it wants EF minus EI. So EF minus EI we can calculate, right? So it will be VTLN. So now since we have a p-type semiconductor, so the excess carrier will be n-type. So it is n-type means ND over NI or del N over NI for the simplification. And this del N can be calculated very easily using the generation rate times constant. Everything is given or not? Time constant is 1 microsecond. So this will be 1014. So EF minus EI will be 0.026 ln 10 per 14 over NI is also given. Yeah, 10. So it is 0.026 ln 10 per 4, which is 4,624.104 times 2.303, something in the order of 2, I guess. Oh, more than 2.3 also. So is there any option? Yeah, it should be 0.24 if I'm not wrong. You can do the calculation, it will come out to be something around 0.24 electron volts. Make sense? So maybe we'll keep the lecture short. So what I did in the initial part of the lecture, I like ran away from the derivation. I mean, ran quickly through the derivation. So if you're not able to understand the problems that we have just covered, you can see the derivation. I mean, the problems are quite easy. But if you can see the derivation once, it will get clear very easily. So for the first part, you can watch in the recording, and after that, the problems were quite basic. So I mean, for I guess for today we can wrap up, and we can meet next time, next week the same time. Any doubts?
Okay,
Yeah. Okay. Fine. Yeah. Any doubts, anyone? Or otherwise, I'll wrap up.
we can. I mean, maybe I'll have doubts next week. I'll study. I'm on bit delay. So
Sure.
last.
Sure. Yeah. Sure. Sure. No problem.
Yeah. So I'm sorry. I mean, I joined late.
No. 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 No problem.